we'll get closer for I work for our Portland team now, so it's like project.
All right, we're gonna go and get organized for the sake of travel a little bit and our online folks. So thanks all for being here. Thank you to Idaho Power. They're here in the back, providing tacos. So if you like tacos, thank them for sure. Yeah, and thank you for them providing this opportunity for us to learn from Nick. I'm really excited about it. I'll make this intro brief so we maximize our presenter time. For those that don't know who we are, we're the Integrated Design Lab, research branch of the University of Idaho Art and Architecture. So we're a mix of research scientists, graduate students, and professors. We just hired a new research student, Annika, this week, so I'm really excited. Always have new faces around, and they keep us young and excited, which is great. Our goal is to be a community resource to you all. We want to help you, design, maintain, operate the most comfortable, efficient buildings, right? And to that end, we have a few resources for free available to you. Also through Idaho Power. So we have our energy resource library, close to 1,000 different tools to monitor how your building is doing. So I know we had a very hot, smoky summer. So if you're worried about a particular zone in your building not keeping temperature, you're getting occupant complaints, but your thermostat still looks okay, we've got some HOMO data loggers that you can set there, just double check that things are tuned correctly. Or if you're trying out a new MER filter on 2 different air handlers, we've got some purple air sensors, so you can measure the difference in particulate matter in the air, how well they're actually filtering out that smoke. All free, available for you to use. We can go out and help you install it, and that's a resource that's available to you. So treat it like a library. Just go to our website page and you can fill out a request. We also have this lecture series, which is great. And just a heads up on our next speaker on September 4th, so coming right up, we're going to have Neil Bolger here talking about VRF systems and Open Studio, something that I know I've struggled with. It can be a challenge, so he's going to bring some light to that. I think it'll be great for our community, both here and online. We also have a couple of online lectures we're presenting from the lab through Idaho Power. So you don't get lunch, but you can tune in and get your PDH credits if you want. This next one is on September 5th that Dylan is providing on luminaire level lighting controls. So each light fixture has its own brain, can really help you meet the energy code requirements in a pretty easy way. So online chat. And then we have our technical design systems program. This is where we work directly with your firm on a particular project or a particular area. And you're like, hey, we want to check out this new type of heat exchanger, or now you're really excited about electric hydronic systems, and you want some more resources, some energy modeling help, so that way you can kind of gain those skills. We will teach them to you. We're educators, we're not consultants or doers. We'll just help you get better at your own jobs. And we can send our grad students off on really interesting and fun research projects along the way. So reach out to us if you want. Thankfully, Idaho Power pays us to have just an open phone, email line anytime you want. So come to us and you're not going to get charged. If it's up to $4,000 worth of our time, which goes for a ways, it's 2 of our work, then we'll write up a proposal to Idaho Power. As long as it meets energy efficiency within the commercial sphere, we're pretty much good to go. You can ask Cherie on that if you want more details. And then if we're going to do like a full teach you how to do energy modeling, simulation, or daylighting analysis, that's when there's a cost share where Idaho Power will pay 75% of our time, and then you or the client pay the other 20%. Pretty good deal. And then Idaho Power also has their own new construction major renovation programs for retrofits, and then their peak flex peak demand response program. Cherie or Andy, do you want to say what you're doing on that?
feel free to reach out to me or Andy and we can talk you through our programs if you're not familiar with them.
And then you are also offering the professional assistance. So help on your time to fill out those incentives, take advantage of them. Then Idaho Power will also pay up to 20% of the incentive or up to $5,000. So it's a great incentive. So yeah, get those applications in early at the very beginning of the design. It's tough to do it afterwards. So I'll stop sharing my screen, and Nick, you should be able to share yours. And it is our great privilege today to have Nick Schmidler with us. He served as the ASHRAE president from 2021 to 2022. He's known for his exceptional service to community, growing the roots of ASHRAE to serve the larger HVAC community and the world. He's chaired the Advanced Energy Design Guide Steering Committee. Those are guides that our lab uses and we recommend to others, particularly for office and hospital buildings looking to save 50% of their operational energy. So Mick is an engineer at Trane. He's been active in the HVAC world since 1982. Received his bachelor's in mechanical engineering from Northwestern and his master's of science in mechanical engineering from the University of Wisconsin. He's LEED certified and he's chaired multiple committees for the U.S. Green Building Council. He's got a ton of accomplishments. I could keep reading, but let me just say that it's a privilege to have you with us here today, Nick. We look forward to hearing from you about efficient hydronic heating and heat recovery systems here in Boise. And it's particularly interesting to us here in Boise, where we have, I think, the largest geothermal distribution network in the US. And there's often questions coming up to our lab around how to optimize this resource and use it in more buildings. So Nick, thank you for your time today. For people that have questions, you can shout them out. Make sure you're able to hear us in the room here. So try to keep the crunching of the taco chips to a minimum. Now you're all getting self-conscious about it. And people online can unmute themselves. But if we start to run long, just kind of censor yourself. We'll try to wrap up by 1 and maybe have a little bit of time again for questions. So Nick, take it away. Thank you.
Thank you so much. It's fabulous to be with you, at least virtually today. Before I get started, I would like to acknowledge 3 different groups. First, our friends in the ASHRAE Idaho chapter. Thank you for your service to our members in the entire industry as well as humanity. Also, I know that you recently hosted the Region 9 Chapter Region Conference in Boise. So thank you for doing that. I got great feedback that it was a fantastic conference. So thanks for doing that. Next, your sponsors, Idaho Power. When we have sponsors, it allows us to provide better reach out to the community. You also give us visibility. So thank you for doing that. And finally, obviously, the Integrated Design Lab. Thank you for reaching out and for putting on the series of talks that you give to help educate the entire community. Now, I did something with my computer, so I might have to look off to my left periodically, but I believe it's working. So you already have the what we're going to cover today. So we're not going to talk about the course description. Next, from a standpoint, we will spend just a little bit of time, 1 slide on both electrification and then on refrigerants. Then we're going to get into the meat of today's presentation. What we're not going to cover are embodied carbon. There are people who know a lot more about embodied carbon, that is the energy that gets into products that you may use. We're not going to get into financial analysis. And the goal today is not advocacy. The goal today is to educate. Whether or not the electrified heating fits you, your clients, your area, fully depends on the particular project. But today, again, is going to be education. I'm going to touch on a difference because many times I hear people use 2 words as if they're the same. One is decarbonization, which is simply reducing the emissions as measured in terms of carbon dioxide or CO2 equivalent. Then there's electrification of heating. And that is, rather than using a fossil fuel at a site, to use electricity, whether that's electric resistance heat or using heat pumps and things like that we'll talk about. That's the electrification. Whether or not they're the same is dependent on a lot of other factors that we will not be going in today. One slide on refrigerant, and this is simply because things are changing, and I want to make sure that you know that the US EPA has a technology transfer requirements out now that as of January 1st, 2025, that's just over 4 months from now, manufacturers we in the United States will no longer be allowed to manufacture or import products, and that includes chillers with a global warming potential of greater than 700. Now, there are some exceptions, but when we're talking about chillers, that means that the GWP of chillers is going to change the refrigerants used already due to past legislation. R123, although it has a low GWP, is not allowed to be used in developing countries. And we will also see 466, 410A, and 134A no longer allowed in chillers. Now, it's also important to know that understand that the industry is ready for this. All the manufacturers have been working toward this, and you will be able to purchase not only minimum efficiency chillers, but chillers that have higher efficiency that are in your codes. Another important aspect is you and your clients are going to be able to install chillers that were manufactured prior to January 1st of 2025. So by December 31st of this year, for 3 years. And there's a whole bunch of other things. Getting all the transfer technology stuff onto one slide was hard, but I think this is the gist of it. So now let's get into the meat of today's program. We're going to talk about electrification of heating, what it is, what it isn't, the types of pieces of equipment you can use, how you may want to put the system together. So let's get started with respect to that. The first thing we're going to talk about is the type of pieces of equipment that can provide a fluid to your building. If we're going to electrify heating, in this case with hydronic systems, we're going to be heating a fluid stream. The first is an air-to-water heat pump, and that could be a packaged air-to-water heat pump. It could be a modular air-to-water heat pump, or it could be what we call a water source heat pump, operating in the heating mode, where we're extracting heat, for example, from a geothermal water loop, and we have a small water source heat pump in each space, and we're providing heat that way. But what these units do is, from the air-to-water heat pump standpoint, generally they will extract heat from outdoor air, use the heat pump, and provide a heated fluid into the building. The other type of equipment is a water-to-water unit. And that water-to-water unit may be what we used to just call a chiller. But a chiller has a condenser. A water-cooled chiller has a condenser, and we heat up water in that condenser loop that can be used for heating. Sometimes you will hear that referred to as a chiller heater. In the summertime, it might be a chiller. In the wintertime, it might be a heater. Generally, when I refer to things as a chiller heater, it does not have a reversing valve, so technically it's not a heat pump. But a lot of people are calling these heat pumps also because they can provide either heating or cooling. The next one, and I'll talk a little bit about this, is a heat recovery chiller. And that is, we're taking that the heat specifically from the condenser water bundle, and we may be able to control to that water temperature to provide heating to our loads. And the third is just an old-fashioned, or what's been around for a long time, is a water-to-water heat pump. So from an air-to-water heat pump example, there's some important things to understand. So this is a graphic, and we're going to use the y-axis for two different things. And on the x-axis is the outdoor air temperature in degrees Fahrenheit. So you will see that the capacity of the unit changes, and it changes pretty significantly as we go from 60 degrees, not a whole lot of change, down to about 30 degrees, but then it drops off very quickly. And in fact, it gets to about half its capacity once we get down to 0 degrees Fahrenheit. At that same time, the power required to produce that capacity at that specific temperature doubles. So when we think of things in terms of efficiency from a heating standpoint, we're going to look at it as coefficient of performance. That is the useful workout, our heating, divided by the power put in and in the same units. So at 60 degrees, the COP is about 4. But as the temperature goes down, the capacity is going down, the power goes up, and we see that at 45 degrees, we're at a COP of about 3. Once we get to about 15 degrees, the COP is 1.5. And when we get down to 0 degrees, our COP is going to be about 1, which is the same as electric resistance heating. The other thing to understand from this graph is that once we get below about 35 or 40 degrees, we lose up to half our capacity. That means we need to, the building owner has to buy double the amount of, quote, cooling equipment to get that heating to get the heating that's required. So it's bad news from both a capacity and cost standpoint and from an efficiency and operations standpoint. And I'll talk more about that in subsequent slides. This is a graph of what happens with an air to water heat pump. And we're looking at both heating capacity, which stays pretty consistent until we get down to up to 125. Okay, so now we're talking about the hot water fluid temperature that's being produced. So until we get about to 125 degrees, the heating capacity stays pretty constant, but our efficiency goes down. Then something happens, and that something is we get to a point where the compressors can't lift the refrigerant from the evaporator temperature, which is cooling that cold outside air, to the condenser temperature, which is providing that warm fluid. When that happens, in order to keep the unit from getting into a bad operating point and affecting reliability and longevity of that piece of equipment, now only one compressor is allowed to operate. So we see a drastic drop in capacity once we get to a fluid temperature where that lift limit is reached. And when we get up to those points, we see that we lose about 60% of our heating capacity and our efficiency goes down by about 1/3. So one of the things this tells us is that we want to choose our hot fluid temperature judiciously. The question isn't what's the hottest water temperature a piece of equipment can make. It's what water temperature can satisfy the loads that we have for this process or for this space. Because as you can see, and we'll talk more about this for other pieces of equipment, as you can see, that hot water temperature affects your capacity and your efficiency significantly. And frankly, it's the one thing that's in your power as an engineer, as a designer, or as a building owner. You don't get to choose what the outdoor air temperature is. You don't get to choose what's happening in the space. The one thing you have when you're designing the system, that one lever, is what's the hot fluid temperature. So that's an air to water heat pump. Now these are different examples of water to water units. In the upper left is a water to water unit using screw or helical rotor compressor technology. Next to that is a scroll compressor water to water unit, but it has 6 pipes. It can provide cooling, a cooling water stream, a hot water stream, and the third one can be hooked up to another hydronic stream, such as a geothermal loop. So this is one unit that called a multi-pipe or 6-pipe unit that has 3 separate heat exchangers and water streams. In the upper right is just a water to water heat pump. The lower right is that chiller heater, but this is with a centrifugal compressor. And the condenser is used to provide heat. Finally, the heat recovery chiller with a separate third condenser, and that third same size condenser helps to separate the heat rejection loop, where we reject heat to the cooling tower when we don't need it, to the heating loop. And that keeps the heating loop clean because the second condenser is a separate hydronic loop. This graphic needs a little bit of explanation. So on the x-axis is going to be the hot fluid temperature, and on the y-axis is going to be the amount of power or energy required to make that fluid. And we're going to take a particular type of unit and show how that changes. Now, if we look at those air-to-water units, the air source air-to-water heat pump, or that water source heat pump extracting heat from a building loop, we seem to see that the air-to-water heat pump power doesn't go up, but that's because we can't add any more capacity because one of the compression units had to stop working. Next, we're going to look at some of the water-to-water units. First, the water-to-water heat pumps are a little bit older technology. Not many of them have been redesigned, so they aren't as efficient at those higher temperatures. Next, screw and scroll compressor water-to-water units. And we see that they are kind of in a similar range, with the screw compressor technology doing a little bit better as the water temperatures increase. And finally, centrifugal compressor technology, generally because of the way the compressors are designed, they'll only get to a little bit lower water temperature in the range of 115 to 120 degrees. Now, the purpose of this is to understand what happens to our power when we have the higher fluid temperature. And when we're looking at things from an overall standpoint, the question is, do we really want to increase our power by 60 to 80%? And the industry is kind of coming around to, no, that's a lot. We see a lot of jobs today designing for heating temperatures, hot fluid temperatures in the range of 105 to 120 degrees Fahrenheit. There's some harder things when you're working with limitations, when you're working with existing systems. And ASHRAE is working on a publication with existing systems, as is the group that I work for. So kind of the industry guidance these days is about 105 to 120 degrees Fahrenheit. Some people feel uncomfortable with those low water temperatures. I can share with you, there's a consulting engineer in Eau Claire, Wisconsin. I live in La Crosse, Wisconsin. Eau Claire is about 2 hours north. He's been doing these systems for years. 15 to 20 years ago, he came to me and he said, we're hydronically heating a building in Wisconsin with 105 degree water. And how do we select a chiller heater? I went, 105, maybe 115 if you think. He said, no, I've done this before. So this isn't a new thing. You aren't going to be on the bleeding edge. We just need to make sure that the system's designed properly. So those are the types of equipment that are available, the effects of ambient temperatures, if we have an air source unit, and the hot fluid temperatures. So perhaps now would be a good point to pause to see if there are any questions before we talk about applying these systems and how to keep them working efficiently. Okay, I'm not hearing or seeing any questions. So let's move on. And right now I can't see the chat. So please, if there are any questions in the chat and somebody wants to bring them forward, please let me know. So next we're going to talk about how you go through and from how you select units. The first thing to understand is, what is the intent of the customer? Do they want to fully electrify their heating? Do they want to do it within a particular budget? Budget will come into place, and we'll talk about budgets in a few slides. And do we want to try to recover heat? For example, do we have a data center on site that operates 24/7? It uses a lot of electricity for that data center. It's going to reject a lot of heat, but rather than reject that heat, can we find a way to use that?
Hey, Mick.
Yes.
Sorry to interrupt. I muted the classroom.
Okay.
So Damon, if there's any questions, you got to unmute yourself.
Thanks.
Here we go. I think we should be unmuted now. Are we unmuted now? Yes.
Yes.
All right. I did have a question before you got into this. Apologies for that.
The question I had was on those graphs that you were showing, is that primarily based on current refrigerants as kind of the standard, or is that across the board, what we would see for the heat pump technology today?
Great question. Some are current refrigerants, some are future refrigerants, some are past refrigerants that will not be available after January 1st. But the general direction is going to be more dependent on the increase in energy is going to be dependent on the compression technology and heat source more than the refrigerant itself.
Okay, thank you.
Thanks for the question. Okay, let's get back in. So we started a little bit. What's the design intent? What does the owner want to get out? What are the project owner requirements? Next, from a standpoint, the hot water temperature that you're producing and choosing, that's the one lever that you have. And the other part is, what's your heat source temperature? I have one slide on geothermal fields, but obviously one of the goal of geothermal fields is we will have different water temperatures available from that geothermal well field than we would from a body of water or the outdoor air. So your heat source temperature is extremely important. Another thing to consider as you're looking at different units is those units will not always be operating at full load conditions. How is that unit, how well does that unit unload when it's making your conditions, the temperatures that you want with the outdoor air conditions, particularly on large jobs? And there are some high profile jobs in your area that do have heat recovery units. They're centrifugal units, but a centrifugal compressor is an aerodynamic device. And the pressure difference that aerodynamic device can produce is dependent on not only how fast is the compressor turning, what its RPM is, but also how much refrigerant is flowing through that compressor. So as that chiller unloads, there's less refrigerant going through the compressor. The compressor can produce less of a pressure difference, and we can actually get to a point where the chiller will enter a regime called surge. And surge is when the pressure in the condenser is higher than the compressor can produce, and the refrigerant actually starts flowing backwards through the compressor. If you've never heard of surge, I've heard it described as a screaming banshee, which it can be. It might shake and vibrate. There are two things when a compressor enters surge is, something's wrong and you want to get out of the equipment room. You can't operate that unit for long periods of time without affecting the reliability of the unit and the longevity. And in fact, the unit can actually tear itself apart. So if it's a larger job and you're using centrifugal chillers, you have to make sure that you know how far you can unload that chiller while maintaining the hot water temperature that you desire, and work closely with the manufacturer on that, and then design the system so you can be ensured that you will have that load when a heat recovery unit is operating. We'll talk a little bit more about defrost, but often when, let's say it's 25 degrees outside and we're extracting heat from the 25-degree air. A lot of times when it's 25 degrees, at least where we live in Wisconsin, it can be pretty humid. When you get to higher elevations, it's not as humid. But as we extract heat from that outdoor air, the air temperature leaving that outdoor unit is colder. And if it goes below the outdoor air dew point, water forms. And if it's below 32 degrees Fahrenheit, frost and ice can form. So in those conditions, the unit has to go into defrost, which is reversing its cycle, becoming a cooler again, and to melt that frost. So you'll have to have some additional units to take care of the heating load when a unit goes into defrost. And you'll also want to make sure that you understand how long that unit will be in defrost. So multiple units could be actually physically separate multiple units, or you could have separate circuits on the same unit type. And again, I have another slide on surge in a couple of minutes. I would say that the best thing that will help you design a system for heating, hydronic heating, is to know what your system loads are. If you have a building automation system that's been historically tracking your cooling and heating loads, fantastic. If you don't, a simulation, a well-calibrated simulation would be great. Outside of that, a simulation may be the best you can do. This load profile shown is for a hospital in a particular climate zone. We're going to use it to look at an example later. And it shows the cooling in blue, the heating in red, from January through December. But the way those loads are lined up isn't very helpful. But if we can get that data and line it up from the highest cooling load down to the lowest cooling load, and then the simultaneous heating loads, we can see where we might be able to do things such as heat recovery. In this case, we would never want to select a heat recovery unit warmer or at a higher capacity than where we have that peak simultaneous cooling and heating load, because then it's going to be operating unloaded. It's going to cost more to operate. It might not be reliable if it's a centrifugal unit. So for heat recovery, I think you'll find when you look at load profiles that your heat recovery unit is often much smaller than you might have thought. Next, if you want to do full electrification of heating, you need to be able to take care of the full design load. But sometimes when you try to do full electrification of heating, the job goes over budget. So at those point in time, sometimes people say, the building owner says, well, we can't do that, but I want to still do significant electrification. So the loads tell you how many hours above what we can afford will we still need to have some backup heating for. So knowing those loads is extremely helpful. And then again, if it's a centrifugal chiller, we'd probably want that unit sized about this place where we have our heat recovery chiller. So the more you know about the loads, the better service you can offer to your clients, and the better your system design is going to be. Next, a lot of the heat pumps that we're using today were designed for cooling and now are being used to provide hot fluids. The bad news, okay, so we know that the load that's being taken care of is the flow rate times the temperature difference. It's proportional to those two variables. But if a unit was designed for cooling, it has a minimum flow rate through that heat exchanger. That minimum flow rate is there to give good efficiency and good heat transfer and consistent heat transfer. So if we go below that minimum, we get poor heat transfer, we get poor efficiency, poor control. So we need to stay above that minimum. But if the minimum was designed for cooling applications, we have that same minimum when we're providing heating. And what usually happens is, due to the minimum flow rate through that heat exchanger, we see that usually the maximum temperature differences from a heating standpoint are about 20 degrees Fahrenheit. Now, in the past, heating systems were often designed for 30 to 40 to even 70 degrees Fahrenheit temperature difference. Now, this doesn't mean that your heating system has to be designed for just a 20-degree delta T, but the unit itself will only to be able to provide that delta T. So you might have to mix some of the unit's water with return water from your system in order to provide the minimum flow rate that that unit can take. As we've looked at this, and this took us a while to go through. We've been looking at the hydronic heating design for quite a while. And many of the cooling hydronic designs have gone to become variable primary flow systems. But if we're already at the minimum flow rate for heating, we can't reduce the flow rate. It's a pretty good idea, if you're in a situation like this, to go back to the primary secondary system because of that heating flow limitation. So a system might look like this, and that is these units here, these air to water heat pumps, can either be in cooling or heating. We have our chilled water loop with a bypass line between the air to water heat pumps and our fluid loop. We have our hot water loop, again, with a bypass line between the production of heat loop and the use of heat loop. Now, how we operate the system, all we have to have, we have a couple valves here at each unit. And if we're going into heating, it opens one of the valve that goes to the heating system. If we're going to be in cooling, it opens the valve that goes to the cooling system. So it's still simple to operate. Another thing that we do, and I don't think I have I don't have the build on this particular one, but we also would probably have a variable speed drive on the pump because our cooling flow rate might be different than our heating flow rate. So the pump speed would also be set to give the proper flow rate depending on the mode that that unit is in. But when we keep the primary secondary systems and we set it up this way, it really is a significant simplification over a lot of the hydronic heating systems that I'd seen in the past. Next, again, a slide about defrost. The first way to take care of defrost is to have multiple circuits in the unit and make it a bigger capacity. Well, that costs the building owner money, so they don't always like that. Next, the more circuits you have, the more capabilities you're going to have to be able to defrost one of the circuits while the others provide heat. So you may want to look at that. You want to make sure that the controls are coordinated so that all the units don't go into defrost at the same time. If it's one particular unit, usually within that unit's controls, it will have those capabilities. But if you have multiple units, then from a system standpoint, you're going to want to keep those units out of defrost at the same time. Finally, if when a unit goes into defrost, it's no longer heating. In fact, it's cooling the water stream. You may want to have some backup heat or a large enough buffer tank so you can ride through the time of defrost. Oftentimes that's in the range of, say, 5 to 8 minutes maximum. So those are some design considerations for defrost. The next thing we're going to talk about is when we're doing heat recovery, the unit placement matters. Many times, one of the things the group I work with does is work with engineers to help design and optimize systems. And many times when people are doing heating and cooling units, the evaporators all end up getting put in parallel. And when all the evaporators are in parallel to produce that chilled water, that means that if the units are different sizes, they will be loaded proportionally. So if we have both a heating unit and a cooling unit loaded, it's hard to preferentially load that heating unit and extract the heat, as much heat as we want, when those evaporators are in parallel. So many times, putting that unit into what's called a side stream position is the best. So this is going to be an example that walks through that. In this case, we have a hydronic system with two 500-ton cooling only units. We have a 200-ton heat recovery unit. and we have a 16-degree temperature difference. But at this point in time, what we need is 550 tons of cooling and 260 MBH of heating. If we walked through all the numbers, first of all, there's plenty of heat to recover and fully load that unit. But if we would walk through the numbers and put those evaporators in parallel, we would see that the maximum cooling capacity, because of the water temperatures mixing, the return water temperature mixing and the flow rate through the heat recovery unit would be about 140 tons. And we would have to purchase additional heat. So we have plenty of heat in the building, but because of the way the system was designed, we can't load that chiller up to the 175 tons needed to make our 2600 MBH. Quite often, the best place to put a heat recovery unit is in what's called a side stream position. In this side stream position, that unit's evaporator has a small pump pumping water through the evaporator. And all it does, it takes water out of the return stream, puts it through the evaporator, and puts it back into the return stream. So we can load that unit only as much as we need to exactly satisfy the heating load. In this example, for example, if we want to make 120-degree hot water with a 56-degree return water temperature and the flow rate for that unit, it only needs to make 42.1-degree chilled water. It's usually going to be less efficient than a larger central cooling unit, so we only want to load it as much as necessary. And this is a case when that unit becomes a heater. So the building load is 550 tons, 2600 MBH. The heater is controlled to provide 2600 MBH. The central chiller takes care of the rest of the cooling load. We don't have any additional heat to reject from the heat recovery unit. That makes the system operation simple. And we do not have to purchase any additional heat. So as you're considering particularly heat recovery, please consider putting the chiller in a preferential arrangement, or in this case, a preferential side stream arrangement. From a building operator standpoint, if they want heat, what do? They turn the unit's pump on. They enable the unit. They tell it to make 120-degree hot water, and they're finished. That is simple. That's reliable. It's efficient. And when people get these and they understand, they go, this is the way we want to design it. Presidential member Kent Peterson said, we can make things elegant. Let's do that whenever we can. So now we're going to walk through a couple examples, and we're going to use load profiles from Pacific Northwest National Laboratories that they did for the ASHRAE SSPC 90.1 committee for the 2019 version. In this case, we're going to have, the first case is going to be a hospital in climate zone 3A. We're going to use Atlanta for climate zone 3A. They need 540 tons of cooling, 3,000 MBH of heating, and their 20-year extreme heating design temperature is 6 degrees. So one of the things in the second example, we'll be looking at a colder climate like yours and mine. But one of the things we need to decide with the building owner is, what heating design temperature are we going to use? Because if we use the 99.6% heating design temperature, that means 0.4 hours of the year, we can't make the heating load. And that's going to be at the worst case. On the second example, I'll show 5-year, 20-year, and 50-year extreme temperatures. But that's one of the conversations that has to take place. In addition, for this particular hospital type and within 90.1, they're required to be able to to recover about 40 tons of heat to preheat their domestic hot water. Other requirements, they have N+1 redundancy from both a cooling and heating standpoint because it's a healthcare facility. That same load profile, that happens to be the hospital in Atlanta. So that's the one we've already talked about. So how can we fully electrify the system and get N+1 cooling and heating? Well, as long as our air to water heat pump can operate down to 0 degrees Fahrenheit, give us the capacity 996 MBH times 3 units, and 200 MBH, 200 tons times 3 units. The 4th unit is for redundancy. And some people, some of our engineers in the group, wait, we needed 3,000 MBH. That's correct. 3 times 996 is not quite 3,000. So the question then is, do we increase the capacity of the unit, or do we redo our heating design calculations? Because 3,000 seems like a pretty round number, and that might not be exactly what it was. But in this case, the system is really simple. We purchased 4 air to water heat pumps. We put them in parallel. We put them so they can serve the cooling and heating loop. We have full redundancy. What is the problem with this hydronic heating and electrification of heating? And in the warmer climates, California heat pumps in general, until you get to elevation, pretty simple. Southeast US, pretty simple. But air to water heat pumps cost more than chillers. So sometimes the job goes over budget. So now we have to go back and say, well, what's another option? Another option could be a modular unit. So rather than having 4 separate units, we have a modular unit that is taking care of a significant amount of our heating, but not our full heating. We'll have to have backup boilers to make up the additional amount of heating and have N+1. In addition, we will have 2 cooling only chillers because the cooling only chillers cost less than the heat pumps. And by the way, generally the modular heat pumps are more expensive than the packaged unit heat pumps, but there are places for both of them. So this would be a design that could balance from a cost standpoint, but only provide significant electrification, not full electrification. Another thing we might want to do, so it would look like this. We have our 2 cooling only units. They'll only send water to the cooling loop. The modular unit sends either chilled water or hot water to the loops. And we have our backup boilers, or backup and the boiler to get us to our design MBH. Another option is to select a heat recovery chiller. So not only do we need the 40 tons of cooling to provide domestic water preheat, we can use that same unit to provide additional heating for our healthcare facility. So in this case, a 120-ton heat recovery unit would get us about 1860 MBH, and at the minimum cooling load, 600 MBH available. We can buy a couple modular units at a lower tonnage to get us to our full heating load, and in this case, we would have full cooling redundancy and heating redundancy as long as we have another cooling only chiller. So we have 3 different unit types, but this might give us a good balance of both cooling, cooling, heating, and heat recovery, and therefore efficiency. And you'll notice that that dedicated heat recovery unit is in a side stream position, both for the cooling stream and for the heating stream. So this is just a summary. We might go in saying we're trying to fully electrify, and it was simple in that case. It went over budget, and we had a couple different ways. One that reduced the cost the most, the other that provided more heating efficiency while reducing the cost. Okay. Now we get to a little bit harder one. It's a secondary school, and it happens to be in climate zone. Wait, that should be a climate zone. Yeah, climate zone 5A, Chicago O'Hare. We have 263 tons, 2,448 MBH, but now our heating design temperature at 99.6 degrees, -2 degrees Fahrenheit. My heat pump stops working, air to water heat pump stops working at 0. My 20-year extreme temperature is a cool -21, and 50 years a cool -26. The hot water supply temperature is 115 degrees. For a school, they need the heating redundancy, but not the cooling redundancy. If they don't have enough cooling, the students get a little bit warm. These are the 5-year extreme temperatures in various locations. I was a little surprised. Boise is 1 degree. Your design heating temperature, I think, is in the range, is like 2.8 degrees Fahrenheit, the 99.6%. This over here, that's the temperature sensor in our house a few years ago when that polar vortex was happening. I got up a little bit late. It was 6 a.m. and it already warmed up to a balmy -34 degrees. But that's when we really need the heat. So again, the discussion to have with the building owner. Cold climate challenges is ASHRAE has a group that has looked at this. The first is in cold climates. We need to advance heat pump technologies. We can't do it with what we have today. Next, some people want to fully electrify, but and think that by saying it, that the laws of physics can be violated. We might need furnaces as backups until we get to all the heating equipment that we need. The electrical infrastructure, Idaho Power. I'm sure you have talks with your clients and customers about this. There are locations where you can't get the power either because of the feeder or the substation. I had the chance about a year ago to go to a workshop put on by a person from a utility. It takes them about 7 years to build a new substation. It takes them 2 years to get the transformers for an additional feeder site. The substation's really expensive. The feeders are still expensive. So the first thing to do if you're looking at electrification of heat is to contact your local electric utility. How much power do you have? What's there? How reliable is it? Because they're going to give you a power budget, because there are other things in that area. Next, supplementary heating, supplementary storage. We're seeing thermal energy storage be used both for cooling and for heating. And then reducing our loads is the best way to make our system efficient. So that's really, we didn't talk about it today, but reducing our heating and cooling loads is the first place to start. And therefore the energy codes are important to do that. So when we're trying to electrify in this climate, we need 3 air to water heat pumps. They can provide heating down, these are packaged units, down to only 25 degrees to make the 115-degree hot water. They're oversized, they're expensive, and we still need a full boiler system to satisfy the heating. How about, so our operation below 25 degrees Fahrenheit for these particular units is all fossil fuel. Is that bad? Well, maybe not. Because, well, those are the extreme temperatures and we need the boilers in those extreme conditions. The average temperatures are much higher and we still can do a lot of heating with the heat pumps. So we need to sometimes step back from, what's the design, what's the worst case condition, and get it to what might actually happen. So significant electrification can still occur. In general, the modular units can get you to lower outdoor air temperatures. So even Boise with your 1 degree 5-year extreme, if you're designing there, you could use this. But if you got below 0 degrees Fahrenheit, you got to a cooler extreme temperature, say at 20 or 50 degrees extreme, you'd still likely want to have some heating units and backup units for heating, but maybe they only need to be designed for not an occupied load, because if it gets down to -20, maybe the school's not in session anyhow. You talked a little bit about geothermal. We're seeing a lot of interest in geothermal, a lot of different technologies. What's shown here is a bore field, a well field, but there are also some technologies where heat exchanges are actually being put down into an aquifer and extracting the heat, but keeping the water loop separate. Disadvantages, they're going to be higher cost, but they're also higher efficiency, so that's great. We're starting to see electrification from a geothermal standpoint. Maybe only a portion of the system is electrified from a geothermal standpoint, which would help reduce the bore field size. I only have one slide about financial impact. There are incentives some places. There are fees some places, which can be, if you will, negative incentives. Be put in just north of the border there. Up in Canada, they have a carbon tax. And then some building owners who have assigned what they call a shadow price for how they value emissions. So as you're working with your clients, consider looking for these various incentives. So general guidance to wrap up here. First, work closely with the design team and the building owner to understand their intent and their requirements. Next, choose temperatures properly. Again, the fluid temperature is about 105 to 120 degrees. Know what your heat source is, how much there is, and how reliable that is. And then I have a master's degree in engineering. I've been in the industry for 42 years. I've seen some electrified heating systems that I do not want to be the building operator for. And I'm not smarter than the operators, but sometimes we get so complex trying to get to the very last kilowatt hour, the very last MBH, that we overcomplicate the systems and they're going to be hard to operate. The simpler we keep the system, more understandable it is, the more likely it is to work. If you're doing heat recovery, really consider side stream. It's our job per 90.1 in the IECC to develop control sequence descriptions. The modes, the different operating modes have to be gone through and done. And again, keep the operators in mind, and if possible, have them on your team. So thanks again for letting me be with you today. I'm going to stop sharing and we'll answer any questions that might have come up. Sorry, I ran us right up to till you're 1 o'clock.
Oh,
So
no,
if
you're
anybody
fine.
needs to leave, feel free.
I think they're gonna unmute in a moment.
Okay.
I'm gonna start our poll for everyone online. If you could please fill that out. And for those of you in the classroom, if you could please make sure you signed in, we would appreciate it.
Dennis, Nick, I have a question.
Yeah, go ahead, Dennis.
Yes, please.
When you were talking about the hospital and you were describing the requirements, you had your cooling loads in tons, you had your heating requirements. But when you talked about the hot water, you switched back to tonnage. Why were you talking about your requirement in tonnage versus BTUs?
Because I think in tons, and I think a lot of the designers think in tons. The number of MBH or BTUs we're going to get out is going to be dependent not only on the cooling load but also the heat of compression. So if you have a COP of 4 for that unit, the unit will make about 1.25 times your tons times 12 MBH per ton. So it's just, in talking with folks, it's easier for them to start with when they're going to use a water-to-water unit. It's often easier for them to think of the cooling side first because that's what they're most familiar with. Fantastic question. Maybe I need to learn more and get better at that.
The other question is when you're talking about defrost and COP, and then also designing on your coldest temperatures, that's when you're gonna go into defrost more. You're gonna need that heat more, and you're gonna have to oversize those or take that in consideration. And when you're, it's kind of a two-part question. That is one. The other one is when you're looking at COP and thinking of the efficiency of it, a lot of people, I don't feel, are probably taking in consideration the defrost mode, because your COP is just gone at that point, right? So the total efficiency of the system.
Yep. So if you have a unit that, it's say a packaged unit with multiple circuits, generally the manufacturer will be able to give you a D rate, maybe like 14% D rate, where you'll still be able to get 86% of the heating out of that unit when one of the circuits goes into defrost. So you can ask the manufacturer about their D rate when they go into defrost. But yeah, we did defrost in like 90 seconds. It's probably at least a 45-minute presentation and discussion when we get into defrost.
Thank you.
You're welcome. Great insights.
A reminder to take extra tacos on your way out. If you're counting on people to eat more. Other questions?
Hi, this is Brendan Gardis out of Atlanta, actually. I had a question on the side stream heat pump chiller application and the considerations on your main chiller unloading when you have that getting you potentially into either a low delta T mode and or unloading your main chiller. And we've had situations where we actually ended up having to turn off the heat pump chiller because there then wasn't enough load on the main chiller. And so we're kind of forced back into a conventional mode at that low load situation. So I was wondering, whether that's different features we should be looking for in the air-cooled chiller, the water-cooled chiller to still achieve part load performance.
Great question. So when you have a unit in the side stream position, its chilled water pump does not add flow to the distribution loop because it's extracting heat and it's putting that heat and that flow rate back into the return line. As you pointed out, two things that does. First, it reduces the return water temperature to the central chillers. So it designed conditions to give the same capacity. Their pumps are going to be sized larger. The chiller selection probably doesn't need to change, but the hydronic pumping needs to be for the full system flow rate. That does, and that return water temperature is dependent on what's the relative size of the heat recovery unit compared to the cooling only units. There were some indoor agriculture systems where they actually decided to do this, where they were both 1,000-ton cooling units. Well, if we have 1,000-ton unit upstream, now it's like 2 units in series. And the entering water temperature for the central cooling only unit is going to be half, or the delta T is only going to be half. So the flow rate has to be a lot larger. In that indoor ag application, that it was okay with them, they had to design for that. There is another way that I didn't show, Brendan, and that is if you have a primary secondary system, not variable primary flow, but primary secondary, if you put that big cooling unit on the load side of the bypass line, now its pump is actually adding water to the distribution loop. So you don't end up with what you described. And that unit can be able to fully load because it always sees the warmest return water temperature. So there are some additional things. We really need to look at them. The larger the heat recovery unit is in comparison with the central cooling only units, the greater the impact is going to be. Very good observation. And again, we can't get into all the details in 50 minutes.
Thank you. Appreciate it.
You're welcome. Thanks for coming from Atlanta.
Got time
Of
for one
course.
last question? Not? Well, thank you very much for your time today. Thank you. It's a wonderful presentation.
My pleasure.
Very, very informative.
Thanks, Integrated Design Lab, Idaho Power, and ASHRAE, Idaho chapter. You all rock. Thanks.
All right, thank you, everyone. Don't forget about our next BSUG next month, demystifying VRFs in Open Studio, September 4th. So we'll see you all then. Have a nice day.
Thanks. Bye-bye.